Good afternoon, Professor.
Good afternoon. Hope everyone's doing well today. We are going to try and wrap up 1.6 today, limits involving infinity. And so last class, the main concept from last class was that when we take a limit, if we ever get a fixed number on top, and it could be either positive or negative, it just depends, divided by something that is going to 0, then whenever that happens, we know that we're either going to get infinity, negative infinity, or the limit will not exist. Okay, and that was also on our little summary sheet. And now we're pretty much ready to move past that at this point. So we are going to the second concept of this section. And as you'll see, it still involves infinity, but it's a completely different perspective. So let's just get started with it. So up to this point, okay, up to this point, if you go back and look at when we first started talking about the limit, every time we've ever taken a limit, we've always said like x goes to, I don't know, some number, right? Like 3, or maybe we said like limit x goes to -2, and we may have put like a plus here or maybe a minus, and that would tell us the left or right side, right? Whether or not we're approaching that number from the left or right. But everything we've done up to this point, the limit, what we're letting x approach, has been a number. So we can imagine that, you know, that number on a number line, right? So here's 3, and in this case we'd be approaching from the right. And on the other one, we'd be approaching -2, and we'd be approaching from the left. But the main idea is that this right here has been a number, right? Now what we're going to do is we're going to say, let's take a limit, but instead of letting x go to a number, we're going to let x go to either infinity, or we may do x going to negative infinity. And this is very different than what we've been doing, because, you know, the number 3, right? That's a number. You can put it on the number line. There it is. -2, you can put it on the number line. But infinity is not a number, right? Infinity is an idea. So what this really means is that what we want to see when we do a limit like this, what we're saying is, you know, what happens, or what's happening, okay, to the function as x gets very big, right? So how does the function behave as x is starting to get bigger and bigger and bigger and bigger and bigger? We can never actually give you a number, because infinity, again, is just this idea, right? But on a number line, what we're saying is, you know, we cannot put infinity here. Does everyone understand it? We cannot put infinity on the number line. But what we can imagine is that the x values that we're plugging in are just going to keep going to the right. So we're just going to keep going bigger and bigger. And what happens to the expression? Now, the only difference between that and the other one is that on negative infinity, it's the same thing. We're saying what happens, right? I'm not going to write this all out again, but what's happening as x gets big but negative, right? Negative. Now, let's just take a look at like the first most basic example, all right? And then from here, we'll build. Any questions on this so far? Okay. So here's your first specific example, all right? What is the limit as x goes to infinity of, let's just say, like 10 over x? Okay, so just like we did before, the first step for doing any limit is to do direct substitution, right? We just see what happens when we just plug in that value for x. But do you see that that's a problem? Like, how do you plug infinity in, right? It's not a number, right? So before we can actually answer this, let's just look to the side here. Let's make like a good old-fashioned t-table. Let's see what would happen if we pick a value of x, and then here 10 over x, that's our function. Let's just plug some values in for x, and let's just let them get bigger and bigger and bigger and bigger and see what happens. So I'll start out with 1. Okay, we plug in 1, we get 10 over 1. That's just 10, right? No big deal. If we plug in, let's say 10, then we get 10 over 10, and that's 1. And then let's plug in 100. So if we plug in 100, we get 10 over 100. And if you do that on your calculator, you'll get 0.1. Let's get bigger, 1,000. If you do that on your calculator, you'll get 0.01. Let's go to 10,000. You'll get 0.001. So you're just going to have to trust me that, you know, as I plug in bigger numbers and calculate that these numbers, can y'all tell what's happening to these numbers? What are they doing?
Getting smaller and smaller.
They're getting smaller. These guys here are approaching what? Approaching. What are they getting closer and closer to?
0.
0, right? So that's the big idea. And this is what you have to kind of make sure that you can process in your head. What we've got here is this scenario. We have something that's fixed on top. Do you all agree that the top is fixed? It's 10, right? 10 is 10. But on the bottom, it's going to infinity. And anytime this happens, anytime you have a fixed number over something that gets bigger and bigger and bigger, that fraction gets smaller and smaller and smaller. Let me say that again. Anytime you have a fraction where the numerator is fixed and the denominator gets bigger, the fraction gets smaller, right? It's like an inverse thing. The bigger the denominator gets, the smaller the fraction gets. And so this is going to go to 0. And that means there's no work to be done, okay? We don't have to do any work. We just have to understand that's what happens. Let me give you another one. What happens if I do limit x goes to negative infinity of 10 over x? Well, what's the only difference here? What's the only difference in this limit?
It's negative. Infinity is negative.
Yeah, we're going to infinity, but we're going negative direction. So if you want to think about it like a number line, in this first problem, we were on a number line. Let's just say here's 0. We were letting x go out this way, right? X was going to the right forever, getting bigger and bigger and bigger. Here on this problem, what we're doing is we're taking x and letting it get bigger, but we're actually going out to the left, right? X is going to go that way. Now, how does it impact our answer over here? Well, imagine each of these are now negative, right? Because you're plugging in numbers that are getting bigger but negative. So I could have changed all these to like -1, -10, -100, -1,000, -10,000. And all that would do over here is change all the answers to negatives. But are they still going to 0? Are they still getting smaller and smaller and smaller?
Yes.
Yeah, now they're negative, but they're still getting small, right? If I keep going down, I might have like -0.00000001 or something like that, but that's still headed to 0. It's a really small, small number. It's just negative. So what we can conclude from this one, again, is that we have fixed over something that goes to negative infinity will also go to 0. All right. So let me bring up that limit summary page that I gave everyone. Here's what we're talking about now. This is what we're referring to today. If you ever have fixed on top, and it doesn't matter if the top is positive or negative, it makes no difference, okay? And your denominator is going to infinity, and actually, it doesn't matter if you're going to positive or negative infinity here. You can add that if you'd like to your sheet. It doesn't matter if that's positive or negative infinity. The whole idea is that the numerator is a fixed number, and the denominator starts getting huge. That limit is 0. Do y'all see there's no algebra to be done here? You don't have to do algebra. You don't have to do a trick. You don't even have to do what we did last class. Remember last class, what we had to do was draw a number line, come in from whichever side, and then start like kind of analyzing what's happening. We don't have to do that here. All we have to do is recognize the pattern, fixed over infinity. Goes to 0, we're done. Okay? Any questions? Let's do another one. Of course, these are going to get more challenging, but hey, how about this one? How about limit x goes to infinity of how about -3 over x squared plus x. Okay, this is a very important problem, okay, because there's little subtle things that are happening here that you have to pay attention to. All right, we're going to try like a direct substitution. When I do that, my numerator is headed to -3. So does everyone agree that my numerator is headed to a fixed number that's negative? So I'm going to put a little negative sign there, right? I have a fixed negative on top, right? Now, on the bottom, think about what would happen if I take a number. I'm focusing all my attention right now on this x squared. What would happen if I take a really, really big number, right? Positive big number, because I'm going to positive infinity. What would happen if I take a really, really big number and square it? It would get bigger, right? Okay, and then I add to that, right? I add to that another big number. That's going to be a big number, right? So where's the bottom headed?
Far away from 0.
Okay, which is where? What do we call that? Real far away.
Infinity.
Infinity. It's headed to infinity. So any big number squared plus another big number, the same big number, is going to give you a really big number. So what I'm trying to get you to see is that all of that is headed towards infinity. And what do we know right away from this? What does a fixed number over infinity head to?
0.
0, and we're done. Okay, we're done. Let's try another one. Okay, please put a little star next to this because this is important. I mean, this is all important. Okay, everything I'm saying here today is important, but this one, students seem to make mistakes on this one. So let's just do this. If we let x go to infinity, of course, the numerator is -3, so it's a fixed number. It's negative, and then over. Okay, so I'm going to call on some people. How about Jean? Is Jean here?
Yes.
Hey, Jean. So my question to you, Jean, is what is happening to x squared if x is getting really, really big and then you square it? What is that heading towards?
That's still just heading towards infinity, isn't it?
Yeah, it's headed towards infinity. All right, good. So I'm just going to put a little arrow here. That's headed towards infinity. Now, Jean, I'll stick with you. How about this x over here? Where is that x headed?
Also still just infinity.
Just infinity. Okay, but here's the difference. I have subtraction. Do you see? We have subtraction between these, not addition. So, Jean, if I tell you, and think very carefully, Jean, about this question. If I tell you I have, I'm not going to say infinity, but Jean, I have this really, really, really big number, okay?
Right.
And then I'm subtracting from it this really, really big number. Can you tell me what that answer would be? Or is that not enough information for you?
That's probably not enough information.
Yeah, it's not, okay? And that's what everyone needs to understand here. Infinity is not a number. So we cannot say that infinity minus infinity is 0. That is not true. Now, infinity plus infinity, see here, this was going to infinity, this was going to infinity, and we are adding them. So if I take a really, really big number and add a really, really big number, I get a really, really, really big number, don't I? But it doesn't work with subtraction. Really, really big number minus really, really big number. Well, you need to know what the numbers are, right? You can't tell me whether or not that's going to be 0 or it could be something else, okay? So the big mistake that students will make is anytime they say infinity minus infinity, they're like, oh, that's 0. No, it's not. You still don't know, okay? So we're at a point right now where we're stuck, all right? We kind of don't know what to do. Now I'm gonna ask someone else here now to think about this. How about Laura? Is Laura here?
Yes, sir.
Okay, Laura. So I want you to think about x squared and x, right? We know that if we plug in big numbers, these both get big. But which one of these do you think gets bigger, x squared or x?
The x squared.
X squared. Do y'all agree that x squared is kind of like dominating the x? If you take a really big number and square it, it's going to be bigger than this number, right? Just the number without squaring it. So it seems like this left side infinity should be bigger than the right side infinity. Seems that way, right? Okay.
I don't know.
Unfortunately, go ahead.
I don't know if I'm thinking about it differently, but if you put like a 1/2, wouldn't the x be bigger than the x squared too? Or if you put like a 1.
Wait, if you do what?
If you plug in like 1/2 for x, wouldn't the x by itself be bigger than the x squared?
Benjamin, yes, you are correct. That is a very good observation. However, Benjamin, where is x headed?
Towards
Where's this limit going? To infinity. So yes, you are correct. When you start plugging in fractions, and this is just a side note for everyone, when you're talking about fractions, most people think that this is true always, that when you square a number, it's always bigger than the number itself. Everyone always thinks that's true. Like 3 squared, of course, is bigger than 3. I agree with that, but it's not always true. And that's what Benjamin is pointing out. If you plug in 1/2 and square it, that is not bigger than 1/2 by itself, because 1/2 squared is 1/4. And that's then smaller than 1/2. So very good observation, Benjamin. But the reason I don't have to worry about this is because we are headed to infinity. So we're very, very far away from the fractions, from 1/2. Is that okay, Benjamin? Good. Okay. So here's where we are. We have this problem right now of not quite knowing how to deal with the infinity minus infinity. Laura has pointed out that, yeah, it looks like the x squared should dominate the x. So how do we deal with this? Well, here's how we deal with it. Check it out. It's actually going to be pretty easy. On the denominator, I'm just going to factor an x out. Does everyone see I could factor an x out of the denominator? Right? X can come out of here, x can come out of here. Now let's just run through this again. We know that as we let x go to infinity, the numerator is fixed number. But now we have, this is headed where? So where's that headed? Just that x. Anyone?
To infinity.
Okay, infinity. But then we have, what's the operation we have next to this?
Multiplication.
Infinity
It's
minus 1.
multiplication, right? We're going times. Now here, think about that number. That would be a huge number, right? Take away 1. It would still be huge, wouldn't it? That'd still be an infinitely big number. So we have infinity here. So now we have infinity times infinity. We've somehow found a clever way of switching infinity minus infinity into infinity times infinity by factoring. And now when you think about this, if I tell you I have a really big number, right, times a really big number, then definitely the answer must be big. Do you agree with that? So with that kind of final little analysis there, here's what I can say. I have a fixed number on top. We know it's negative because it's going to -3. And on the bottom, it's headed to infinity because I know that those two together multiply to be something really big. And then I know that the answer here is 0. What do y'all think? It's okay so far?
You don't have to worry about multiplying the x with the -1.
Oh, you mean distributing? No, because I'm looking at these as like two different things. Like here's x, that's really big. And then I'm looking at x minus 1, all of that together is just a really big number, right? Because think about, let's say x is like 40 trillion, right? If I take 40 trillion and I subtract 1, that's pretty much still 40 trillion, right? And infinity is actually, the idea of infinity is even further and further away from 40 trillion. It's just, it's forever in that direction. Infinity is a weird thing. Is that all right?
Yeah, I understand.
Okay. All right. So let's go to another example. Things are going to start to get weird here. Let's say, oh, you know what? Let me do this. I'm going to give you a major note or result here. Okay. I'm just going to call it a note. Okay, everyone. Anytime you have a limit as x goes to infinity, whether it be plus or minus, it doesn't matter if it's positive or negative infinity. And what you have is a constant, which I'm going to call c over x to the power n. This limit will always go to 0. As long as n is greater than 0. So let me write that down, and then I will just show you with some examples underneath it. If I take the limit as x goes to infinity of 5 over x to the third, let me just write a couple of examples down here, and then we'll run through them. Okay, all three of these are examples of this right here. We have a number on top, a constant on top. Okay. We have x going to infinity on, well, here I just did infinity. I could have used negative infinity. And then do you see that every one of the denominators is just x to some power n? Oh, what about that last one? What's the square root of x? What's another way we can write square root of x? X to what power?
It's just x.
Isn't
Oh, no,
that
no.
the square
To
root
the
of
1/2
x?
power?
One?
1/2.
Oh,
1/2
yeah.
power.
Yeah.
Okay,
1/2.
that's what square root of x really means, x to the 1/2. So the power here is a half. So this little note is saying, look, if you've got a fixed number on top and you've got x being raised to a power and x is going to infinity, the answer is going to be 0. Now, I did say here that the power had to be greater than 0. So this only works if you have like positive numbers here, 3, 7, 1/2. It works. If those go to negative numbers, things change. Any questions on that? The whole idea is fixed over infinity. That's what you're getting, fixed over infinity. So it's going to head to 0. All right, here we go. We're going to now go to where things start getting kind of weird. Limit x goes to infinity of x plus 1 over x plus 3. I'm just going to give you a second to write it down and think about it. Claire, are you here? Claire? No Claire? 3, 2, 1, no Claire?
Hey, Professor.
Yes.
Just a quick question. So what if we don't have here in this like statement, we don't have plus or minus sign? Like,
Where?
let's say we have a different sign, like we have a divide or anything like that.
What do you mean, where?
Is it possible? Like where you put x plus 3, what if we have a x divided by 3 here?
Like x over 3 here?
Yeah.
We could still take a look at it.
Okay.
Because if we had x over 3 on the bottom, that's really 1/3 x, right? That's what x over 3
Right.
means. And then this would still be going to infinity, right? And 1/3 of infinity is still infinite,
Okay.
right? Because I mean, you take half of infinity, you basically still have half. I mean, you still have infinity. It's still a huge number. It's weird. I mean, right? It's just the number keeps getting bigger. So multiplying it by half isn't going to really change the fact that it's going to keep getting bigger.
Okay. Just wanted to make sure. Thank you.
Uh-huh. Okay, so no Claire. How about Braxton? Oh, wait, no, hold on. Sorry. I'm trying to get people who have only been called on twice. Vivian?
Yes.
Okay, Vivian, can you tell me what the numerator is doing and then the denominator?
Yeah, for the top one, the x is gonna be infinity, so the number is getting bigger.
Mhm.
So is the bottom.
Yeah, and so is the bottom. So Vivian's saying, look, what's happening here is we're getting infinity on top and infinity on the bottom. So Vivian's saying, look, that's getting big, right? X is getting big and we're adding 1. So if you add 1 to infinity, well, it's still a huge number, right?
Yes.
And if you take a number that's huge and you add 3 to it, it's still a big number. So that you're getting infinity over infinity. Now, just like before, this is not, these aren't numbers. So you can't just say, oh, those cancel out and it becomes a 1. Like, no, you cannot say that because these are not like fixed numbers. So we have this new form that we have not seen. Have we seen this yet? Right? Right? We have not seen this yet. So let's go to our little formula sheets or a little limit summary. And let's see, we've done that, and we've done this too. 0 over 0, we need some algebra, some trick, but hey, look at that right next to it. Infinity over infinity. If we ever see that, guess what we get to do again? Algebra or trick. Okay, so here it comes. Now I have to start showing you these new types of tricks in algebra that we're going to do whenever we see infinity over infinity. Here it comes. Okay, so when you see infinity over infinity, what you're going to do, the normal rule of thumb, okay, I hope I've kind of made it clear to you that in a calculus class, there's never, or very seldom is there like a rule that always works, like you always do this. But for this problem, infinity over infinity, what you want to try first is looking at the denominator and look for the highest power of x that you can find. So we have x to the first power there, right? We have x to the first power. So what we're going to do, and just do it, and then I'll explain why we're doing it. What we're going to do is we're going to take this limit and we are going to multiply the front of it by a 1. Okay, so I'm going to multiply this whole thing by 1, which I can do because 1 doesn't change anything. But the one that I'm going to choose is going to be 1 over x over 1 over x. Okay, now let me write it down and then we'll talk about why I'm doing this. The reason I chose 1 over x is because the power on that thing in yellow, the power on that x was 1, right? So that's why I did 1 over x, not 1 over x squared or 1 over x cubed. I did 1 over x. With me? Okay, now let's see why I did that. Let's multiply that through. We got to do it on the top and on the bottom. I'm about to call on somebody to tell me what I get when I multiply through. Also, I'm writing the limit down again. So I'm going to distribute that through. So what happens when you multiply 1 over x by x? So when you multiply these together, what happens? 1 over x times x.
Can anyone answer, or do you have to?
Hey, go ahead, anyone.
When you multiply it, you're only changing the numerator. So for 1 over x times x would be x over x.
X over x, which is?
It's b1.
1. Okay, so we get a 1 there, right? So we get 1. And then we do plus. Now we're doing 1 over x times 1.
Mm-hmm.
Well, anything times 1 is itself. So I have 1 over x there, right?
Yes.
Okay, now on the bottom, let's do the same thing. I'll call on someone on the next example. 1 over x times x, we do that again, right? We get 1. And then we have plus. Now when you do 1 over x times 3, you get 3 over x. Do y'all agree? Okay, now the reason I did this is because I'm now going to use this property. Anytime you have a constant over x to a power and you take this limit as x goes to infinity or negative infinity, this will go to 0. And do y'all see that we have somehow created 2 of those right here? Do y'all see we've created 2 of them? constant over x to a power. So let's let x go to infinity now. So no more limit. I'm going to let x go to infinity. This 1 is not impacted by x at all. So I'm going to have a 1 there. Plus, now this is headed where?
To infinity, which kind of means 0.
It's headed to 1 over infinity, or fixed over infinity, which is headed to 0, right? So that's headed to 0 over, now on the bottom I have the 1 there, and then this guy is also headed to 0. So that's a plus 0. What we like to say is that these two things here, they vanish, okay? They vanish. As you take the limit, those basically go off to 0, and so you're essentially getting 1 divided by 1, which is 1. So the limit of that is 1. Now I'm going to show you visually. Oh man, maybe not.
Professor, real quick, I had a question. So if you were to like, because you know how you said you immediately start with direct substitution. If you were to have immediately started with it, and like you said, like it'd be infinity plus a big plus 1, it'd just still be a really big number. Plus infinity plus 3, also just again a really big number. Would that be? Would you be able to do 1 no, right? Because you don't know what the numbers are.
Yeah, I know I just told you that infinity over infinity is not 1, and then our answer was 1, but that just happens to be the answer here.
Okay, cool. Yeah.
Yeah, we'll do another example where we won't get 1. Okay.
Okay, thank you.
All right, so look, what I'm going to do now is I'm actually going to graph that thing as a function. What was it? X plus 1 over x plus 3? Wasn't that what it was?
Yes,
Yeah,
sir.
that's what it
Here's
was.
here's the graph of that, okay? Here's the graph of that. It's a rational function from college algebra. And what I want you to see is that if I graph the horizontal line, y equals 1, there's y equals 1. If you notice here, if we go out to the right, do y'all see what the function is doing? It's getting closer and closer to 1, isn't it? It's getting closer and closer to 1. In college algebra, what did we call this blue thing that goes across?
Horizontal asymptote.
Horizontal asymptote, right? Horizontal asymptote. So that's exactly what we just found. We found the horizontal asymptote of this function. You don't really realize it when you're doing the calculus that when you take the limit as x goes to infinity, you're finding the horizontal asymptote, but that's what we're doing. All right. You might remember this in college algebra. You might remember that when they gave you a function, like if they would have given you the function f of x equals x plus 1 over x plus 3, and they ask you to find the horizontal asymptote, what you do, and if you remember it, great. If you don't worry about it. You compare the degree of the numerator and denominator. So they both have the same degree, 1. So what you're supposed to do in college algebra is then look at the number in front of this one and the number in front of this one, and then make a fraction out of those, 1 over 1. And that's your horizontal asymptote. If you remember that, that's the way we did in college algebra. Now in calculus, what we're going to do is do a limit. All right, let's do another one. Limit x goes to infinity. Let's do 3x squared plus x minus 1 over x squared minus x plus 1. All right, here we go. We got to take our time through this. Is Gabriel here?
Yes, I'm here.
Okay, are you following, Gabriel?
Yes, sir.
Okay, so what I want to know, I'm just going to kind of point at each of these, and then you're just going to kind of tell me where they go as x goes to infinity. So how about this one right here? Where does that go?
You mean positive infinity?
Positive infinity, so that's going to infinity. And then we have plus. Where's this one going, Gabriel?
Infinity.
Infinity, so we're adding those together. And then we have minus 1, right? So what do you think that's going to turn out being, Gabriel? Infinity plus infinity, take away 1.
Not sure.
Big number plus big number, take away 1, still big number?
Yes.
Yeah. So this top part should be headed to infinity. Do y'all see that? Because we had infinity plus infinity, and then take away 1. Taking away 1 doesn't do much, okay? Has very little impact on things. And then we're dividing that by, okay, let's go to Alex. Is Alex here? Alex Soto? No? No? Okay.
Axel, sir.
Oh, I'm sorry. Yeah, that's my fault. Axel, my fault. I just didn't read properly. Okay, Axel. Axel, where's that headed?
To infinity.
Okay, infinity, and then minus, this one's headed to
Infinity.
infinity, and then plus 1, right?
Yes.
Now, Axel, we have infinity minus infinity. Can we just tell, if I just tell you infinity minus infinity, can you tell me that that's 0, or is that a problem?
No, it's a problem because you don't know the numbers.
We don't know the numbers, but Axel, you can tell me which of these dominates, right?
Yes.
Which one of those is going to dominate?
The x squared.
The x squared. So that means that this infinity here is going to overpower the other one. So I showed you that we could factor it earlier, but we just need to now know that because that one's x squared, it's going to overpower the other one. And so we don't even need to take that one into account. Can you all be okay with that idea?
Yes.
Okay. And then we're going to add 1 to that, right, Axel?
Mm-hmm.
Okay, so the bottom, infinity plus 1, still infinite, right?
Mm-hmm.
All right, good. So we have infinity over infinity. This is bad. We need some algebra. We need some sort of trick. So I'm going to go ahead and start getting myself set up for the next step. I'm going to rewrite the problem.
So Professor, why are we eliminating that x? I'm sorry, yeah, that x.
We're not eliminating it. What we're doing is we're ignoring it, because even though it gets bigger, and even though I'm subtracting it, this x squared is so much bigger than the x that it doesn't, taking away that x doesn't impact the fact that it's still getting big. Really big and really positive. Is that okay?
Yes, sir, thank you.
Okay. In fact, if we would have had this x cubed minus x squared, this would be infinity minus infinity. But because x cubed dominates x squared, we would ignore the x squared and just go with the x cubed. So as long as the power is bigger than the other one, then it would dominate. Okay? All right, so we're at this point where we have infinity over infinity, and now, let's see, Javier, is Javier around?
Yes, I'm here.
Okay, so Javier, do you remember kind of what I said? Whenever we have infinity over infinity, one of the things you can try and do is what?
And algebra trick.
Okay, so what is the algebra that we did on the last problem?
So we look for the highest power in the denominator.
In the denominator, which is?
X squared.
X squared, okay. And then from that, I'm going to multiply out front by what?
By 1.
Yeah, by 1, good. And how am I going to write that 1?
Like in the next step, I think it would be like 1 over x squared.
Perfect. 1 over x squared over 1 over x squared. Okay, we're using x squared because that's what was here, right?
Right.
And now when we do this, good things should happen, all right?
I have a
Good
question.
things should happen. Yes.
Do you always multiply by 1?
Hmm?
Do you always multiply by 1?
Well, I have to multiply by 1 because anytime you multiply anything by 1, it doesn't change the problem, right?
Okay.
So that's why I have to use the 1 over x squared over 1 over x squared, because it's 1, right? So I'm not changing anything. I'm just making everything look different, which is kind of tricky, isn't it? Like we're just manipulating this. We're massaging the expression to make it look the way we want it to look. It's tricky. Okay, let's distribute here to here, here to here, here to here. So I'll do the top one, then I'm going to call on someone for the bottom one. When I distribute that through, I'm going to keep my limit here. Okay, when I distribute through 1 over x squared times 3x squared, the x squareds cancel, I'm left with 3. Okay, then when I do 1 over x squared times x, just one of the x's cancels, so I'm left with a 1 over x. And then 1 over x squared times -1, I'm left with minus 1 over x squared. Over. Is Mostafa here? No? Okay. I do realize that some of you are sending me stuff in the chat, and quite honestly, I can't do that much multitasking. So I apologize if I'm not getting to you in the chat. All right, Austin, how about Austin?
Yes, sir.
You doing all right, man?
Yeah, been better.
I wasn't feeling that great earlier too. Okay, but it seems like whenever I start talking about math, I always start feeling better. That's kind of a sickness I have, I think. All right, Austin, how about going through the denominator? If you distribute here to here, what do you get?
Just one.
1, okay. And then when you go here to here?
It's going to be 1 over x.
Minus 1 over x.
Right.
And then plus 1 over x squared on the last one?
Yes, sir.
Okay, you're off the hook, Austin. All right. Good job. Danielle, you're up.
Me?
Yep, you. I have a Danielle and a Daniela. So I'm at Danielle right now. So Danielle, what happens here? What happens to this, 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 and this?
They could cancel out.
How do you mean?
Added? I mean multiplied? I don't remember.
X is going to infinity, right? Each one of these is a fixed number over something going to infinity. Fixed over infinity, fixed over infinity, fixed over infinity. All of those will go to
0? Oh, wow.
0. Yeah, that's the major idea today. Anytime we have fixed over anything that goes to infinity, that will go to 0. And so what we've done is we have made a couple of these pieces do that. And so now this vanishes to 0, vanishes to 0, vanishes to 0, vanishes to 0, which leaves us simply the 3 over 1, which is 3. Danielle, does that make sense?
Not even one.
All right, anybody have any questions on that? I'm about to do another one.
So the signs between them don't matter, do they?
Don't, because it's going to be, you know, you're adding or subtracting a number that's going to 0. So you're adding nothing or subtracting nothing, right? So it has no impact on things.
Okay.
Wait, so like you said in algebra, you could find the answer from the equation just from looking at it.
Uh-huh.
Oh, got it.
Yeah, but I'm going to give you an example today where your algebra won't work. So just be careful. Yeah. We're just not ready for that example yet. I need to build up to it. Okay, so here we go. Next one, x squared plus 1 over 4x cubed plus x. Give everyone a second. I'm going to go refill my drink, and I'm going to give everyone a second to kind of see if you can't go through this on your own a little bit. See if you can go through, like, at least get to this step here where you come in with the 1, and then I'll call on someone. Let's just take like 3 minutes.
What did y'all get?
I'm at the part where he wants us to be left off on, like the 1 over x squared, except it's not 1 over x squared, it's 1 over x cubed.
I got 2.
What's up?
I was gonna say I got 2 over 5 over 1 over x, something like that.
Oh, I'm still working on mine.
I don't know if it's 1 over 6x squared or not.
I'm gonna start working it out without saying anything. I'm just gonna work it out, and then you can look at it and see if you're getting the same sort of thing. I stopped intentionally because I want to make sure people know what happens on this step. So does anyone want to share with the class what you get when you multiply that 1 over x cubed through?
Do you want the numerator or denominator first?
Give me the numerator. What's 1 over x cubed times x squared?
I got x squared over x cubed, but that turned out to be 1 over x.
Okay, good. Good. Everyone needs to understand that. When you multiply those first two, 1 over x cubed times x squared, this is the same as x squared over x cubed. And then you can just use properties of exponents. Basically, 2 of these x's go away, and you just get 1 over x. Okay. And then on the second one, it's just 1 over x cubed times 1, right? Which is just 1 over x cubed.
Yep.
Okay. You want to keep going?
I'll do one more and I'll give someone else a chance.
Okay. What do you got on the bottom?
For the bottom, I had 4x cubed over x cubed, but I simplified it further to be 4 over 1.
4 over 1. So I'm just going to put 4. Okay. Then plus
1 over x squared.
1 over x squared. Good. Okay, does anybody have a question as to why we had infinity over infinity? Why I came in with 1 over x cubed over 1 over x cubed? Any questions on that?
I have a question, like for, say if you had like an x to the 4th power, would you do 1 over x to the 4th power?
Yep.
Like you try, okay. But I tried pulling out the x at the bottom.
Okay.
And then doing 1 over x squared.
Yeah. No.
Okay.
Okay, now let me call on somebody. Gage, are you here?
Yes, I'm here.
Hey, Gage. Of everything that we have written down now, what things are going to vanish to 0?
Wouldn't it be everything except for the 4?
That's right. So this is going to go to 0. This is going to go to 0. This is going to go to 0. So very carefully, Gage, tell me what I would have left in the numerator. What's still in the top?
Would it be
0, right?
0, right? Which is
Yeah, 0 plus 0, right? So you're going to have 0 on top. And on the bottom gauge, what are you going to have?
The 4.
4. And 0 divided by 4 is not a problem, okay? 0 divided by 4 is 0.
Mhm.
And so your answer is 0. You can't have 0 on the bottom. You can have 0 on the top, but you can't have it on the bottom. And that's why we always look at the power on the bottom to pick what we're going to do out here. Because by picking the power on the bottom, we're guaranteeing ourselves that one of these pieces on the bottom is not going to be 0. It's a little subtle thing. If you don't see it, it's okay. But that's why. If you want to know why we pick x cubed here, or 1 over x cubed, and why we pick 1 over x squared, and why, you know, why I'm doing that, it's because you don't want to have zeros all on the bottom. That would be a problem. You'd have division by 0. Okay, so that limit is 0. Okay. We keep going. Limit. X goes to infinity of x squared plus 1 over 3 minus x. Excuse me. Cody, where's the numerator headed? Cody? No, no Cody. All righty. Is Fiona here? No Fiona. All right. Emmanuel?
I'm here.
Okay, so where's the numerator headed, Emmanuel?
Be headed to infinity.
Okay, and then where's the denominator headed?
Would that also be heading towards infinity? But
It would be. However, just to be careful here, this is headed to 3, and then you're subtracting a number that's headed to infinity. So if you take 3 and take away a huge number, do you agree that that would be negative infinity?
yes.
Okay, that does not change anything, okay? If we have infinity over infinity, it doesn't matter if it's positive or negative, doesn't matter, okay? Anytime we see infinity over infinity in any form, we are going to say this is bad, okay? All right, Emmanuel, you want to keep going or you want me to move on to someone else?
I can keep going.
Okay, so since you've got this situation, you need to come in here with something out front, right? So what are you going to do here? What's your 1 going to be? It's 1 over something, 1 over something.
It'd be 1 over x squared, right?
You've got to look at the highest power of x that you see in the denominator. Always the denominator. So just x, okay?
Right.
You clear? All right. So 1 over x, and now we just distribute through. So here to here, here to here, here to here, here to here. All right, I'm just going to write out what it is. So limit x goes to infinity. On this first multiplication, be real careful here. 1 over x times x squared is x squared over x, and one of the x's cancel, so you're left with an x. And then 1 over x times 1, you're left with plus 1 over x. Then on the bottom, 1 over x times 3 gives you 3 over x. And then this one, 1 over x times negative x gives you negative 1. Any questions on that?
How did we get the 1 over x when we distributed to x squared? I can't do the math.
This times this,
Uh-huh.
get the x, right? Is that what you're asking?
Yeah, like yeah, like when
1
we
over
ended
x
up
times x
distributing it. I guess just the simple math that goes into it.
1 over x times x squared, just put the x squared on top and then just cancel one of the x's here with this one.
Okay, thank
Right,
you.
because x squared over x is really this, x times x over x. So one of the x's cancels.
Ah, okay, I see now.
Yeah. Okay, Emmanuel, you're good. Matthew?
I'm here.
Okay, Matthew, what vanishes to 0? Which of
The
the
1 over x on the top and then the 3 over x on the bottom.
Okay, so Matthew, what are you left with then?
An infinity on the top over.
Yeah. Yeah, this is the first time this has happened to everyone. So watch, I'm going to write the limit again. And the reason I'm writing the limit again is because we still have an x in here. In all the other problems, the x's have gone away and we've been left with numbers. But in this case, we still have an x here and we need to let it go to infinity. So Matthew, if I let x go to positive infinity now, the top's going to go to infinity, right? It's getting bigger.
Yes.
Divided by -1. So what's that going to be headed towards?
Negative infinity.
Negative infinity. And so our answer is negative infinity. So this is the first time we've actually got an answer that has infinity in it. See, our answer is not infinity over infinity. Our answer is infinity. Negative, sorry, negative infinity.
I have a question.
Yes.
Why isn't the x 0 or infinity? Well, wait.
Why isn't, which x? This x?
The first one, yeah.
The reason that doesn't, so you're asking me why doesn't this one vanish and go to 0?
Yeah.
Because it's not a fixed number over x.
Oh.
See, the 1 over x is a fixed number over x, right? The 3 over x is a fixed number over x. We know that as x gets big, this gets small, goes to 0. As x gets big, this gets small and goes to 0. But as x gets big here, it's not part of a fraction. It's just x, so it gets huge, right?
Yeah.
And then you divide by -1, and that creates a negative huge number.
Okay. Got it.
Got it? Okay. All right, I have another example for you. All right, so now we have something different. All right, this is different because we have a square root in here, right? It's going to change things a little bit. But as we've been doing, let's go ahead and just let x go to infinity and think about what happens. So as x goes to infinity, 4 times infinity is infinity. Plus 1, right? So the top heads to infinity. Over. Now, here we have infinity squared, right? Big number squared, it's infinity plus 1. So do you all agree that everything that's under the root is becoming infinite? Right? Infinite there. And how about the square root of infinity? What do you think? Take a huge number, take the square root of it. Isn't it still a big number?
Yep.
It's smaller than it was, but it's still, if it's getting bigger and bigger, that's going to keep growing, right? So just because we take the square root does not change the fact that the denominator is also going to infinity. Any questions? All right, so if we have infinity over infinity, what we're going to try and do is we're going to try and multiply by something out front. We're going to try and multiply by a 1, right? And here is where you have to pay attention. There's something different in this problem, all right? So I told you to look at the highest power of x, right? And in the denominator, which would be x squared, right? The whole idea here is that we would like that x squared to cancel out. If you look back on all the problems we've done, the thing that we chose, right, the yellow thing, we picked 1 over it so that when we multiplied it through, it would give us a number. Same here with this 4x cubed, we did 1 over x cubed. So when we multiplied through, we got 4. Here we had x, we did 1 over x because when we multiplied through, that became a 1. The whole idea was to try and make that thing in yellow become just a number. And then everything else, whatever happens, happens. So here, I want that x squared to go away. So do you all agree I need to divide it by x squared? So I have to do like a 1 over x squared?
Yep.
But there's a problem, because if I put 1 over x, excuse me, if I put 1 over x squared out here, if I try and multiply this through, there's a square root in the way. Do y'all see that? There's a square root in the way. I can't just push that into the root. I have to do something with the root, okay? So this is not going to work. So to kind of motivate this and to get you to understand what's happening here, I want you to think about something. When you were learning about radicals back in college algebra, if you were ever asked to find, let's say, the square root of x cubed, hopefully you were taught that that can be rewritten as x squared times x. And then because you have an x squared in here, and this is a square root, you could pull that x squared out as an x in front of the root. Is that kind of the way you learned it?
Yeah.
Your head a little bit? Yes.
No.
Not really?
It's been years.
Okay, well, it's algebra, so we have to be able to do algebra to do calculus. So that is a property of radicals that we need to be comfortable with. But not even this. This is not what I want you to see. I want you to see something different. But
Oh, I was just joking, by the way.
oh, okay, okay.
Real.
Let me do it this way. If we have square root of 8, we can rewrite that as square root of 4 times 2. And then because the square root of 4 is 2, we can bring the 2 out and it's 2 root 2. Does that look more familiar? Maybe?
Yes.
Is it gonna be 1 over 2 square root x kind of thing?
I hear someone running towards my
Is that what that is?
Over for this?
Uh-huh.
Not
one-
quite. Not quite.
Okay.
Let me finish this idea and then maybe we can figure out what's going to happen here.
Okay, thank you.
So look, what I would expect everyone in this class to be comfortable with at this point is that if you have something under a square root that's squared, it comes out unsquared. Like, so I have an x squared under here, I can pull it out as an x. If I have a 4 under here, I can pull it out as a 2, right? Yeah, yeah.
Yes.
Okay. What we want to do is the opposite. We want to start with something on the outside and we want to push it into the root. So let me ask you, what happens to something if you want to push it into the root? We know that when you take it out, you take the square root of it, right? But when you push it in, what happens to it?
Yes.
It becomes squared.
It becomes squared. Okay, that's critical. Think about it this way. If this 2 right here, if I wanted to put it back under the root, I'd have to put it as a 4, wouldn't I? So I'd square the 2 to push it back in. If I want to get this x back in here with this x, I have to push it in, but it has to become an x squared. So what you need to do is think about this over here. You want to be able to push something in the root that when it goes in, it's 1 over x squared. That's what it needs to be once it's inside. So what does it need to be on the outside?
1 over x to the 4th.
We're going to square it on its way in. We're squaring it on, not square rooting it on its way in, we're squaring it on its way in.
It needs to be x.
Just 1 over x. That's it. Think about this. If I ask you to square this, right? Take 1 over x and square it, what would it become? Take 1 over x and square it. Just square the top and bottom, 1 over x squared, right? Square the 1, square the x, you got 1 over x squared. So I'm going to come in with the 1 over x on the outside, and that way when I push it into the root, it's going to become the 1 over x squared that I need to kill off the yellow. I'm going to write the next line. I think I'm going to go ahead and on the numerator, I'm just going to pass 1 over x through because that's the easier part. This goes to here, we get a 4 and then plus 1 over x. Now on the bottom, this is the part that's a little strange. I'm going to write square root. And then here comes my 1 over x is going to go inside, become 1 over x squared when it goes in. And then it still has to multiply through to everything that's there. So that 1 over x goes in here, becomes a 1 over x squared. That's right there. And then I have to pass it through everything that was underneath this root. So it has to distribute through to all of these. Square root's still there. Okay, when I distribute, I get a 1. Next one, I get x over x squared, which is 1 over x. And the next one, that's just 1 over x squared. And there it is. Any questions? I know that this is weird first time you see it, but any questions?
Could you scroll up a bit more?
But okay.
Yeah.
Let's see, I'm trying to get through everyone here today. Brian, I don't think I've called on Brian yet.
Well, I volunteered like.
Oh, you have, yeah, never mind. You volunteer. How about Braxton? Braxton?
I don't think you've called on me today yet.
Not yet? Okay. So Braxton, I was just going to ask you, what out of this thing vanishes away? When we take our limit, what's going to vanish?
The 1 over x in the numerator.
Okay. What else?
Can't see the, scroll down just a little bit. The 1 over x and the 1 over x squared and the square root in the denominator.
Okay, so Braxton, then what's left?
For 4 over square root of 1, so that would just be 4 over 1, and then that would be 4.
Good. The answer is 4. Weird problem, huh? So just be aware, this is the big note for this, okay, is that if you ever have a square root and you need to kill something off in here like the x squared, you're going to have to think about what it is you put on the outside so that when it goes in and gets squared, it'll kill off the x squared. I forgot who I had asked earlier, but someone had said 1 over x to the 4th, which is very common. First time you're seeing this, that's what you may think. But if you put 1 over x to the 4th here, okay, I'm talking about right here, then when it goes in, it would become 1 over x to the 8th. And then that's a problem, because then if you can do it yourself, okay? If you do 1 over x to the 8th through here, then everything on the bottom vanishes to 0, and then you get division by 0, which doesn't get you anywhere. Okay, you get basically stuck. So just be careful. All right. There's still more to talk about, all right? Okay, now we're going to take a look at this one.
Isn't that 1?
I was hoping someone would say that. Is it 1? What do y'all think?
I feel like it's still junk over junk. So if we abide to our principles, it would still be 1.
Okay, so we do have junk over junk, right? This is sign of junk over junk. I agree that the junk matches, right? But what was the other condition about the junk? Where did the junk have to be going? Has to be going to 0. Is our junk going to 0?
Nope.
No, it's going to infinity. So do not mistake this problem with this one. Limit x goes to 0 of sine of x over x. That is 1, and I agree. But because we're going to infinity, different things happening here, right? So let's talk about what's happening. Let's do the denominator first, okay? The denominator, obviously x is going to infinity, so that's headed to infinity, so that's infinite, right? But what about the sine function? The sine function, as you go to infinity, think about what the sine function looks like.
It repeats.
It does this, right? So as you go to infinity, as x goes to infinity, is your sine function headed to one specific number?
No.
No, it just keeps oscillating, right? It keeps oscillating. And so what we have here is a situation where our numerator, now don't write this down, but this is what we have. Our actual numerator limit doesn't exist because it's not headed to anything. You'll buy that?
Yes.
So this is not even infinity over infinity. Okay, this is not infinity over infinity. This is basically something where the limit doesn't exist divided by infinity. But I do want to point something out. Would you all agree that the sine function is bounded? And what I mean by that is something you learned in pre-cal, and you can tell from the picture that sine of x, no matter what it is always between -1 and 1. That's something you learn about the sine function in pre-cal, the range of the sine function. The highest it goes is 1 and the lowest it goes is -1, right? So it's always stuck between those two numbers. It's at different values depending on x, but it's always bounded between those, yes?
Yes.
Okay, so what I'm going to put here on top here is a word I haven't used yet. I'm going to use the word bounded. What we have is a bounded function on top and a function that goes to infinity on the bottom. And anytime you see this, the answer is 0. Right? Always. So I'm going to go back to that formula, the summary sheet. And when you look at these, pay attention to this one right here in yellow. I say fixed, positive or negative, right? Over infinity, the answer is 0. But do y'all see what I wrote down here about what I mean by the word fixed? I say here, fixed actually means either a non-zero number, so it could be like the number 5 or -3 or 10 or something like that, and or bounded. So when I say fixed in this little sheet I made you, I really mean either a number or a bounded function. So, yeah.
About the sine function, what if you put like an x in front of it for like the amplitude? Would that still be bounded? If the amplitude.
You want me to leave? Are you saying, okay, so you're saying, like, look at a whole new function, x sine x, like that?
Yeah.
That would not be bounded.
Okay.
That would not be bounded. But fortunately for us, we have just sine x, right? Okay, so we have sine x over x. This is bounded over infinity. Anytime you have bounded over infinity, it's going to go to 0. Now, I think it's worth looking at this function. Like, I want to graph this for you because I want you to see something. Yeah, there's kind of a cool little thing that's going to. So here's sine x. That's the regular sine function, right? Okay. Now, sine functions are good at modeling like real world behavior, right? Things that happen in the real world that are periodic. So one example, and this, I don't have anything in the room, but think about if let's say that our x-axis, let's say is time, and then let's say our y-axis is height. And let me add 1 to this function to move it up. And let's just say that we're looking at this curve as being measuring the height of a basketball. So I'm going to take a basketball and I'm going to drop it, right? And the clock starts. So I drop it. So time goes in the ball, the height of the ball comes down, it hits the ground, bounces back up, and then hits the ground, bounces back up, right? Then the sine curve is pretty reasonable in terms of showing what the ball's doing, right? Except for the fact that in the real world, we know that the ball actually doesn't come all the way back up, right? It starts to get, less and less and less till it finally goes and stops moving, right? So maybe we can come up with a function that would do that. Well, all I have to do is take this sine x right here and divide it by x. And I'm going to have to move the 1 out. No, I can. Yeah, let's just look at this. So this one's a little hard to see it, but it's still a sine curve. It's still a sine curve, but what's happening is as time goes on, the amplitude of the sine curve is getting smaller and smaller and smaller. So it's more like a real ball. It starts off and then it bounces, doesn't come back up quite as high, and then a little less, little less, little less, little less, little less. That's what's happening here. Bounce, not as high, not as high, not as high. These are called dampened oscillators because you're dampening the bounce. So this is more like a real world problem. And can you see that when we look at it, as you go out further and further and further, can you tell that the graph is headed towards 0? It's kind of like funneling towards 0. That's a good way of showing it. So what I've done is I've graphed two functions here, a purple one, a black one. That's 1 over x and negative 1 over x. And if you look at our sine curve always stays between those two. And so it's like we've created this funnel that the sine curve's trying to do its normal bouncing, but it has to stay between these other curves. So it dampens it. Okay, I won't get more into that. That's definitely engineering sort of related perspective on things. Dampened oscillators. All I want you to know from this is anytime you run a limit and you get a bounded function on top divided by infinity, your answer is 0, all right? It's headed to 0. All right, what time we got? 2:17. Okay, let's do another one. Limit x goes to infinity. X squared minus the square root of x. So if we do this, figure out what's going on. We've got infinity here, right? And then minus, and then here that goes to infinity. So we have infinity minus infinity. And which one of those do you think dominates?
X squared.
X squared. X squared is definitely going to dominate square root of x. Would you all agree? Is that pretty straightforward?
Yes.
Okay, so here I'm just going to put, okay, this one dominates. So my answer should be just positive infinity. Now, keep in mind that if I did it this way, what would our answer be?
Negative infinity.
Negative infinity, because now we're doing, this one goes to infinity and we're subtracting infinity, but this one's dominating, so I should have a minus infinity, not plus. Make sense? Because it's being subtracted. Okay, now try this one. Trying to get something similar to what's in the homework. Okay, let's think about what's happening. Infinity squared times 16 plus 1. That should be an infinitely big number, right? The square root of that should be an infinitely big number. So all of this should be headed to infinity. And then minus 4 times infinity, that should be negative infinity. Now, is it clear to you or not which one dominates?
I think the left side one slightly dominates.
You think
by
so?
1.
So the x squared would make you think it dominates, right? But then you're taking the square root. So if you take the square root of something squared, then it's basically like there was never a square on it, right? And that means this would be like just a 16x almost. Does that make sense?
Yeah.
Square it, then square root. So this is kind of like almost the same expression. So unfortunately, we cannot do what we did in this one, where we just look at it and go, oh, this one obviously dominates the other one. We have to do something else. And so there's nothing obvious to do here, I don't think, but I'm just going to close my eyes and hope somebody comes up with the right way to go. So just based on what you've learned in this class so far, like you've got to step up to the plate and do something. Like just somebody give me something.
You mean a made-up problem?
What do you mean?
I don't know what's being asked. Sorry.
Oh, I'm saying we're
Did
stuck.
you do 1
I'm
over x
saying we're
squared?
stuck, and I want you to tell me what you want me to do. Go ahead. What? I didn't hear that.
I said that
Could you do 1 over x squared?
1 over x. Okay, I know where you're coming from. Someone else said something else though. I want to be.
I was saying what you meant
Okay.
by like someone step up.
Okay, so Braxton, I think, is suggesting that we come in here with a 1. Is that what I'm understanding? Do like 1 over x out here?
Yeah, I said 1 over x squared, but I don't know which one would work better, or if it would even work.
Yeah, so here's the problem. We do that when we see infinity over infinity. That's what we will do. That's what we'll try. All of these problems that we've done so far in class, it was always infinity over infinity, infinity over infinity, infinity over infinity. Now we actually have infinity minus infinity, but we can't tell who wins. On the previous 2, we could tell who won.
Is there any way we can make them to infinity multiply infinity?
That means you would have to factor them.
Right.
Right? Maybe.
I have another idea. I don't know if it would work. Could you actually like try to put in x value and see what it equals? Like put 16 and in place of the x, put 1 and
just
like
start
see what it
plugging
equals.
values in to see. You could, but there's the danger in that is we want to know what happens as x goes to infinity. So you may pick a number and it may tell you what's happening near that number, but that doesn't tell you what's happening further out. So maybe you pick 100. Well, 100 is too far away from infinity. So maybe you try 1,000. Well, 1,000 is still really far from infinity. So you can't be sure that that's the answer. So then you say, I'm going to put 1 billion, but 1 billion is still very far away from infinity, right? Because infinity is like incomprehensible. I can't say it. I can say incomprehensible. No, I'm trying to say incomprehensibly large. Is that a word? Incomprehensibly?
It is now.
It is now, yeah. It's unfathomable. Whatever. Anyway, so look, I could let you stare at this for a couple of weeks maybe, and I don't know, maybe you'd come up with this, but now I'm going to show you algebra trick. Here we go. Ready? Conjugate. But see, we have a problem. We don't have a fraction. So we can't do like conjugate on top and bottom. So watch what I do. Here comes the conjugate. I can't just do the conjugate on the top without doing it on the bottom. So I have to realize I'm looking at a fraction here. And I treat this as this being over 1. Now that's pretty unnatural, isn't it? To just do that out of nowhere like that. But let's see what it gets us. All right, because I came in with the conjugate, when I do this to this, the roots go away. So I'm just left with 16x squared plus 1. The middle terms I ignore, right? I just completely ignore the middle terms. And then what about these two multiplied? What do I get there? Is that negative 16x squared? Are you all with me? I feel like I've lost y'all here.
Yes.
Yes, I've lost you, or yes, you're with me.
No, we're with you.
Okay. Any questions on the expanding of that and cleaning it up? Do y'all see what happens?
Yes.
Do you see that those go away? Okay. Now, let's run the limit. Let's go ahead. Let's let x go to infinity. Let's talk about where things are headed. I feel like I haven't gotten to everyone here today. Well, Dilpreet, you're up. So do you want to tell me where the numerator is going?
It's a fixed number, so
Fixed, right? 1, good. I'm just even going to write fixed because I'm even happier that you said that. Fixed over, okay. Dilpreet, where are things going here? Where's all that going?
to infinity.
Okay, and then
This is also a positive infinity.
infinity, and we're adding them, right? We're adding them. That's not a problem. It's when we're subtracting them that we have a problem. So we know that the bottom's headed to infinity. And Dilpreet, what happens whenever we have a fixed number over infinity? Where does it go?
0.
0. So this limit is 0. But we had to come in here with this conjugate. Really weird. Really weird.
For the top one, did you FOIL or you just like?
I did FOIL, but because it's a conjugate, I don't have to do the middle terms,
Oh, okay.
right? Because if you were to have done the middle terms, which would have been this times that would have given you an answer. And then you do this times this, and basically everything in the yellow would have canceled with everything in the blue. And so that's why I didn't do that multiplication. That's the beauty of the conjugate, is that you don't have to worry about the middle terms.
Okay.
Okay. Okay, we have one more thing to talk about. I still have 12 minutes. This is it for this part. So the next part is going to be completely different. All right. So what I'm going to do is I'm going to write down a bunch of things, and I want you to draw a graph that satisfies all of these things. Okay, so I would like for you to sketch a function f such that all of these conditions are met. First, A, I would like the limit as x goes to negative infinity of this function. I want it to be infinity. The next thing I want is that the limit as x approaches -3 from the left of this function to be 4. I'm going to write a lot of things down here. The limit as x approaches -3 from the right of the function, I want that to be -1. I want f of -3 to be 0. I want the limit as x approaches 2 of the function to be 2. I want f of 2 to be 0. I want the limit as x approaches 5 from the left of the function to be infinity. Almost done. I want the limit as x approaches 5 from the right of the function to be 3, last one. I want the limit as x approaches infinity of the function to be 0. All right, here we go. You have to draw a function now where all of these things are true. Now, I should point out, everybody in this class is going to have a different answer. Like your pictures are going to look different, but they will all have these properties or characteristics in common. So here's my graph. You all ready for me to go through this? Or do you want me to give you like 3 minutes to try and draw it yourself? It's up to you.
I thought we were gonna go into breakout rooms, but all right.
We can do that. We can do that. I mean, what do y'all want? Yeah, why don't I do that? I'll just break you out real quick, and then I will, while you're in there, I'll draw mine, and then you will come back and see if y'all's, looks anything like mine. Here we go. There you go. Enjoy. I'll pull y'all back here in about 7 minutes. About 20 more seconds and everyone will be back in here. Okay, so first things first, on our homework, you should now be able to do all of 1.6 homework. I would say omit number 41 and 49. Just don't worry about those. We're not going to cover that. We're not even going to mess with it. So just get rid of those. So you should be able to do everything up through 33 now. All right, on the homework. Now, in terms of the problem I just gave you, here's my drawing up to this point. And remember, I'll send these notes to you later so you can come back and look at this if you want. What I've done is everything in red is the function that I've drawn. And next to it, I put A, B, C, D, and that corresponds to what I was trying to draw. So like for this first one, I needed to draw the function so that when I went to negative infinity, that means out to the left, I needed the graph to go up to infinity. So I just drew a little like curve going up. Okay. And then condition B, I needed the limit as I approached -3 from the left to be headed to 4. So I drew a little graph headed into -3 from the left that it's headed towards 4. And I did that for all of the different conditions. And then my last step would be to connect all these things together to make a function. So I would just connect, and connect. So I'll entertain questions on that at the beginning of class. If anyone has any questions, we can talk about that on Tuesday. But for now, here is a solution. Yours could look a little bit different, but it should generally look the same as mine here. Okay, class is over, so you're free to go. Have a good weekend. Make sure you do your homework, and yeah, enjoy the Super Bowl. Hopefully, it'll be a good game.
Okay,
Thank you. Have a good day.
Have a
Okay.
good weekend, Professor.
Thank you.
Bye,
I'll hang
thank
out
you.
for a minute if you have a question.
Mine looked very similar to that one. I was just in the middle.